what I've shown you works for one dimension, but it also will work for more than one dimension, which shouldn't be a surprise. This vector stuff is still going to work, but I want to say just a little bit about that. So let's look at a top view of like a pool table view, or even air hockey, a top view of an air hockey table where we have a puck and it's coming along and it hits another puck, maybe similar mass, different mass, maybe they stick together, maybe they don't. Or maybe we've got two pucks. Actually, I'll do two pucks colliding into each other. So I've got one kind of coming like this, and they come together right about here, and they bounce off of each other like this. And maybe this one goes sort of more this direction. So this is the initial, and this is the initial, and then they end up over here, final, ended up over here, final. And again, this is a situation where for the whole system, right, let's see, this whole system, we need to be able to say that the sum of the external forces needs to be 0. So if we're looking at this from above, we want to make sure the normal is balanced by the weight, so we don't have a tilted table, for example. But if it's a flat table, so that the normal force and the weight isn't making these float down to one side of the table or another, then we can look at this and we can say, hey, we can still use conservation of momentum. It just gets more complicated. So we can talk about initial momentum as actually having momentum for particle 1. Let's say this is particle 1 and this is particle 2 is equal to particle 1 initially plus particle 2 initially. They have x and y components. And so what we do is we break these into components. So the x component would be initial momentum, or m times v of 1 in the x to start with. This is like so crazy number of subscripts here. Plus particle 2, momentum of 2, its x component initially must be equal to what's happening in the y, in the final in the x direction. That's 1, that's 2. And then the same thing is true in y. In other words, this p initial is equal to p final of, p final of p1 final plus p2 final. Somehow I changed my subscripts here. But this is really saying these two things are equal, this is equal to this, is two equations, one in the x and one in the y, and they both have to be true. So what this means is that if I set this up, right, this is my m1, the initial, and then this would be mv1y, this is mv1x, this is the initial. And then I've got this over here, right? So I've got something like this, m2, m1, v2 in the y direction, and then there's going to be a minus because it's down, initial, and then m2 v2x initial, again, probably I'd call that the negative direction. Then if I add these two together, that has to equal the sums of the components of the final situation. And so formally, this is just going to look just like this other equation. I'll write it out. m1 vyi plus m2 vy initial equals m1 vy final plus m2 v2y final. And using the signs that I have over here, for example, I would say this one is positive, and for this setup, this is negative. And then when I get on the other side, this one is going down, so this would be negative, and this one would be positive. So I would set up my equation something like this. And I can do the same thing up here. I can write this as mv and all of that. But you got to keep your signs in there. So if this is negative, make sure you're keeping those signs and decide what is the positive and negative direction. So It's the same thing we did before. We had to watch signs before, but it's messier because we've got multiple equations, which of course gives you multiple places to sort of lose some signs. So just keep things well organized so you can keep track of what you've got, what information you have, and what you don't have.